We just learned that the proximal convoluted tubule is able to reabsorb 2/3 of the fluids that were filtered at the collective glomeruli. So that means out of the 180 liters of fluid that are filtered at the glomeruli, the proximal convoluted tubule is able to reabsorb 120 liters of that. Still, 180 minus 120 is equal to 60. That's 60 liters of fluids, and we can't afford losing that much fluid. So we need another mechanism. Now we're going to get to the countercurrent multiplier. So we're using the loop of Henle and a mechanism of alternating water and salt permeability to reabsorb massive amounts of fluid. In order for the water to be reabsorbed, the interstitial fluid must be hypertonic, and we're going to provide that by pumping salt. The osmotic pressure of the interstitial tissue fluid is 4 times that of plasma, and that results partly from the fact that the tubule bends, permitting interaction between the descending and ascending limbs. This sounds very theoretical, and it is. It's easier to look at a picture. So here is the loop of Henle. After the proximal convoluted tubule, we're going into the loop of Henle at approximately 200 milliosmoles of dissolved particles. Now, the descending limb of Henle's loop is the first part right here. That first part is only permeable to water. Now, water is going to move where the salt is. Water movement is driven by osmosis. We're only going to be able to achieve water movement if we put a high salt concentration in this area right here. Well, how do we get a lot of salt there? Well, at the ascending limb of Henle's loop, the back end right here, this end is permeable to salt, but not to water. So now we're going to use active transport of salt. That's these pumps right here that you see. These pumps will pump lots and lots of salt out of the ascending limb of Henle's loop. They put the salt surrounding the descending limb of Henle's loop, and now since there's so much salt, the water is drawn out of the descending limb of Henle's loop and is put back into the capillary. This is a great mechanism. It works like a charm, and it reabsorbs massive amounts of salt and water, mostly the water. Now, the one thing is it's called countercurrent multiplier because basically we have to start at the back end. The water isn't just going to leave from the descending limb of Henle's loop if it's not for all that salt that's surrounding here. So we need to first put the salt here into the descending limb of Henle's loop area, and then the water will go out by the masses. But that means we need to start back here first. So basically we need to start pumping salt before we can draw water. And so it's basically the back end that we need to start out with. Now the fluids do come by here on the descending limb first. But the whole system has to start somewhere. And when it's all in place, it works beautifully. So you have that high salt concentration surrounding the descending limb of Henle's loop, and then the descending limb of Henle's loop is only permeable to water, so water is drawn out by the masses and put back into the capillaries, into the cardiovascular system. And then so you can see how as we're losing water, the osmolarity of the fluid here increases from 600 to 800 to 1,000, 1,200, even 1,400 milliosmoles. Now we have highly concentrated stuff, and it makes it easy here on the back end, on the ascending limb of Henle's loop. We have so much to work with. We have tons of salt coming by here. We can just pump it out and just basically refuel the system. So as we are losing salt, now the back end here, the ascending limb of Henle's loop, is only permeable to salt. And so therefore the salt is being pumped out, and no water can follow because it's not permeable to water on the back end here. And so as this very highly concentrated fluid comes by here, we are pulling out salt by active transport and putting it into the descending limb, and that will be losing the water. So take a look at the permeabilities. That's very important. On the descending limb of Henle's loop, we have permeability to water only. And the ascending limb of Henle's loop, we have active transport of sodium chloride salt. And we are impermeable, not permeable to water. So on the ascending limb of Henle's loop, we're pulling out all the salt. We're going from 1400 to 1200, 1800, 600, 400, 200 even. So by the time we're leaving Henle's loop, the fluid is actually less concentrated than the fluid that went into the loop of Henle, and we have been able to reabsorb massive amounts of fluid. So take a look at this, let this sink in for a little bit. It's not the easiest concept, but this is the loop of Henle, and it's called countercurrent multiplier. So here we have the whole thing one more time because it's such a beautiful system. So we're arriving out of the proximal convoluted tubule here at 300 milliosmoles. We're going into the descending limb of Henle's loop, which is only permeable to water, and we're drawing out massive amounts of water because there's such a high salt concentration here. So we're going from 600 to 800, 1000, 1200, even 1400 milliosmoles concentrated fluid. So massive amounts of fluids, water that is, leaves here the descending limb and is put back into the cardiovascular system. And then on the back end, at the ascending limb of Henle's loop, we're permeable to salt. We're pumping out salt actively. These are all salt pumps, and so therefore the concentration of the salt in the fluid declines from 1400 to 1200, 1800, 600, 400, 200. So by the time we're leaving the loop of Henle, we are very dilute, and then we still need to reabsorb more fluids because we're still not done. It will be still too much to excrete. Now, before we move on, let me just emphasize this one more time. Make sure that you take a look at the permeability differences. On the descending limb, we're permeable to water only. On the ascending limb, we are actively transporting salt, and we are not permeable to water. So make sure that you understand that. Okay, so let's now move on to the third step in the series of filtration, reabsorption, secretion. So again, filtration and reabsorption are huge. 180 liters right here, and the reabsorption is 178.5 liters per day. Now secretion is minuscule, but it's still important. So secretion is sort of your final opportunity to get rid of a little bit of trash. Mostly it's some active secretion of substances that you didn't want anymore, and it's an inward movement. That means we're putting stuff into the renal tubules right here. So it's the secretion of substances from the peritubular capillaries back into the interstitial fluid and then transport into the lumen of the tubule and ultimately into the urine. It allows the kidneys to rapidly eliminate certain potentially toxic substances. It also allows for regulation of pH if you need to do that. So the secretion is the transfer of molecules from the extracellular fluid into the lumen of the nephron tubules. It's an active process, and it's very important in the homeostatic regulation of potassium and hydrogen ions. So here you have the hydrogen ions, that means pH regulation. Increasing secretion enhances nephron excretion. It is a competitive process, and substances such as penicillin that are foreign to your body, how would it know how to reabsorb that if it's not a naturally occurring substance in your body? So a lot of drugs, penicillins, they need to be secreted, so they need to be actively get rid of via your kidneys. And basically what we have here, the mechanism of how organic molecules, something like penicillin, might be transported from the interstitial fluid into the tubular lumen. So tubular lumen is right here, and you have a whole bunch of pathways in which something like this could be happening. I don't want to spend much time on this. So this is basically, you should know that organic molecules that your body wants to get rid of, it has an opportunity to put that into the urine via secretion. Now moving on to excretion. So excretion is the final volume that leaves your body. So it's the result of the mechanisms of filtration minus reabsorption plus the secretion, and that's the amount you excrete, that you actually get rid of. Now, before we talk about the exact mechanism, how you get rid of these fluids that then need to leave your body, let's take a look at clearance. Clearance is important clinically. It's the rate at which a solute disappears from the body by excretion or by metabolism. It's a way that pharmacologists measure how certain drugs are being excreted, how they're leaving the body. And so you need to have some sort of a baseline, and that baseline is usually inulin or creatine that are used to measure the GFR, the glomerular filtration rate, and then measure the clearance of a certain substance. So at what rate something is leaving your body. So here are some examples given. I don't want to spend a whole lot of time on this, but basically, so you're establishing a baseline of the clearance of a substance by using something that you know how it is being excreted. And so that would be the inulin excretion. And that gives you a baseline of how a certain substance is processed, and then comparing to inulin, you're taking a look at whatever substance you are interested in, and then comparing it to the clearance of inulin, and that gives you sort of an idea of how fast something is processed via the kidneys. So here with the inulin, you get 100% of the inulin is filtered in the glomerulus, and then it's getting processed, but 0% of the inulin is reabsorbed. That means 100% of the inulin is excreted. That means the filtered load of inulin is equal to the excretion rate of the inulin. That means that the GFR, the glomerular filtration rate, is equal to the excretion rate of inulin, and is equal to the inulin clearance. So that means GFR, the glomerular filtration rate, is equal to the inulin clearance. Now the book is giving you some useful equations here for renal physiology, and that's this table, but here basically just the first one is important for you guys. The excretion is equal to filtration minus reabsorption plus secretion. We talked about that. These here are more clinically relevant equations that maybe in if you go to medical school or nursing school, that might be important. Now let's take a look here at the glucose clearance. Glucose is completely filtered, so that means 100% filtration at the level of the glomerulus. So this will be 100% filtration. And then you want to keep your glucose, it's a nutrient. So now 100% of the glucose is reabsorbed. That means 0 glucose is excreted, and we should achieve exactly that 100% reabsorption. That always works unless you have way too much glucose in the blood. In diabetes, you have way too much glucose in the blood. It still gets all filtered here at the glomerulus, and your renal tubules, they're trying to reabsorb 100% of it, but they will not be able to achieve a glucose clearance of 0 milliliters per minute. And that means some of the glucose will end up staying in the renal tubules because your glucose transporters are simply maxed out, and you end up excreting some glucose in the urine, and that's where you can measure it. Urea clearance is an example of a substance that a waste product. On the other hand, it is still useful for osmotic pull. And so here we have a substance that is completely filtered at the glomerulus, but then 50% is reabsorbed and 50% is excreted. So here you have sort of a mixture of some is reabsorbed, some of it is excreted. Now in penicillin, we have the clearance. Here we have an example of net secretion, the penicillin clearance here. We do filter out some at the glomerulus. Some of it stays in the blood. Some will be then secreted, and we have no reabsorption mechanisms. So you do end up with penicillin metabolites that you can measure in the urine. Here at the end, the elimination of urine from your body, it's called Micturition. At rest, the bladder here, the external sphincter is contracted and no urine is leaving your body. And when the bladder fills up, then this mechanism sets in. the stretch receptors will fire, and then the parasympathetic neurons fire. So there will be this input here towards the smooth muscle, and then the smooth muscle contracts, and the urine will be released from your body.